about how we use stellar standard candles in this distance ladder measurement. Of course, Adam just brilliantly introduced the topic and showed how you get really to the most precise measurement to date. In my group at EPFL, we've been focusing quite a lot on different types of systematics and different ways that this measurement of the Hubble constant could be potentially biased in some sense. And today I will essentially tell you that we don't have cause for concern from all we've seen. We've been trying to break this measurement, but it's really very hard. And in the end, most of what we do is in the end refining the measurement, making sure that the systematics are at the same level as they're stated. But as I would like to, as I'm speaking to a different crowd than I'm usually speaking to, I'd like to first start with simply the point that what we're looking at are standard candles. And a standard candle is kind of an empirical object, right? It's an object that you can calibrate the true luminosity. So you know how bright it is intrinsically, and then it really doesn't matter what it's made of, whether it's the oil from a sperm whale, as it used to be for a real standard candle, or whether it's an LED light bulb or a star for that matter. As long as you can calibrate the luminosity and you measure how bright the object appears, you know that by the inverse distance squared, the flux that you receive is reduced. And so the whole trick is to calibrate these standard candles. So in the Hubble constant measurement that Adam described, we basically have a two-rung distance ladder measurement that uses two types of standard candles. The first one are the type 1a supernovae that are extremely luminous stellar explosions that we can use to really map out the isotropic expansion of space in the Hubble flow. And here you see a supernova shining brighter even than the host galaxy itself. That's why we use the type 1a supernovae, because they're so intrinsically luminous. So this is where we really map the Hubble flow. But then, of course, we don't have any type 1a supernovae whose true distance we know directly, because we don't have any galaxies to which we already know the distance trigonometrically or from geometry. So we require an additional intermediate step to calibrate the luminosity of the supernovae. And for this, we use these supernova host galaxies that Adam mentioned. And in this kind of galaxy here, you see M101, the supernova 2011 FE is completely obvious, right? It's very easy to see. The Cepheids in this galaxy are much more numerous. There's about 500 of them in this galaxy. But you really only see them once you turn on the time dimension and you actually look for the variability. And it's really nice because these objects have a very characteristic variability that is easy to identify. It has characteristic timescales, characteristic amplitudes, and so you can really very nicely identify the objects. And thanks to Henrietta Leavitt's work from the beginning of the 20th century, we know that the log of the period correlates with the true luminosity. That's why oftentimes we'll refer to this period luminosity relation as Leavitt's law in her honor. And this is what we calibrate on this very first rung, where we tie this Leavitt law to geometric distances. So for example, we have the Gaia parallaxes that are something fairly new, but currently the most accurate. We have the LMC's distance and then NGC 4258. And so in a sense, what we're doing by using these stellar standard candles is we're tying back the Hubble flow measured by supernovae to the angular scale provided by parallax and other geometric distance measurements. And in this way, we can really tie this distance ladder into cosmology. Now, there's another kind of standard candle that we can use to calibrate the supernovae, and that's the so-called tip of the red giant branch method, or the TRGB. And the TRGB does exactly the same thing that the Cepheids do, it just works a little bit differently. And so in particular, you look at these color magnitude diagrams where you try to get this axis here calibrated on an absolute scale because you know the distance. And what you're looking for is the disappearance of stars. And there's a physical motivation for this. It's actually the helium flash that occurs in red giant stars that essentially prevents objects from becoming more luminous than this step. So the star will evolve up to this point and then back down again. So the TRGB as a feature in a color magnitude diagram is really marked by the absence of objects. But you can calibrate this point, and then if you can identify the same kind of feature in another galaxy, all you're looking for is the distance modulus mu here between this apparent magnitude and this absolute magnitude. That's the definition of the luminosity distance. And so using galaxies that host type 1a supernovae, once you measure these TRGB features, you can create the same kind of Hubble constant measurement, and that's the basis for the Carnegie-Chicago Hubble program's TRGB-based distance ladder. So it's really using the same concepts. It's simply replacing the Cepheids with this TRGB feature here to calibrate the absolute scale. So we're trying to measure the Hubble constant to 1%, and of course this requires very detailed control of the systematics involved. And in particular in my group, we're focusing on these two first rungs here, so this absolute calibration of the distances, and then how we very precisely and without introducing any bias can apply them to calibrate the supernovae. And it's particularly interesting to focus on this part because that's what ends up dominating the uncertainties on the Hubble constant. So in turn, this is where we hope to have the greatest benefits. But let's revisit quickly which kind of standard candles we have and why. So the classical Cepheids Adam introduced are really excellent objects for doing this. And in particular, because every Cepheid can very easily be measured, you identify every single object by its period and light variation, and you can calibrate that even on an individual level using the parallax measurements for every single Cepheid. You have the characteristic variability, you can understand the scattering, the PL relation, and there's very minimal contamination by any objects that you're not interested in because they would not fall on this PL sequence, or they would not have the characteristic period you're looking for. And even in terms of stellar evolution, these objects are very well understood, much better actually than a TRGB feature, which would depend also on a star formation history in a given galaxy, for example. So I would tend to maybe distinguish two types of standard candles here. We could say we have individual standard candles, and I would count the classical Cepheids among those because we can measure the individual object. But then there's other kinds as well. For example, there's the Myra variables. These are very good contenders for a James Webb-based distance ladder because they're infrared bright and have very long periods. So there's quite a lot of work going on in this direction. Our Lyrae stars are great for near-field cosmology, things like the makeup of the Milky Way or the local group, but they're a bit limited in terms of the distances that we can pursue because they're not so luminous. There's other types of pulsating stars that you can also use to measure distances, but they're not competitive with the Cepheids or others. And then we have statistical standard candles that rely on a specific feature in a color magnitude diagram that you want to identify in the same way in different environments. And the Typilar giant branch is one like this. That's currently the best alternative to Cepheids. And then there's another one that has been more recently suggested. That's the so-called J-region AGB stars. That works very similar to the TRGB, is extremely interesting for James Webb because it's a very infrared bright type of methodology. But these are carbon-rich, very dusty stars, and we don't yet have that good of an understanding of this. So I would put it under the category of great for the future, but we need more data, of course. And so what it looks like in terms of diagrams is that in an individual standard candle, here you have a sample where each of the red points, for example, is one of these cluster Cepheids Adam was talking about. Each of these stars are measured individually, whereas in this TRGB feature, you have a complex color magnitude diagram, and you try to identify this line shown here in blue. That is always going to be a little bit more involved of a measurement because you don't have control over the actual population that you're measuring. So let's get to some of those details, and in particular how we get to this absolute magnitude capital M here that we can calibrate if we know the distance. And let's start with the parallax measurements provided by the ESA mission Gaia that has really been transformative in this field in the last few years. Unfortunately, I have to start out with a little bit of a downer. We have systematics in Gaia that are known that are at the level of about 20 microarcseconds, which is about a 10% error at 5 kiloparsec distances. So we're inside the Milky Way, we're measuring individual star parallaxes, and we have a systematic error that is larger than what we would want it. So thankfully, there are quasars and other stars to which we could calibrate these types of issues, and the Gaia collaboration by Leonard Lidegren has actually provided a methodology for calibrating out this problem. But in the end, what it leads to is that most analyses that use Gaia parallaxes have to solve for a residual parallax offset that applies to their sample. and they pay a penalty for it. So we're trying to sound out this problem by using the stellar oscillations by asteroseismology. So this is really using the frequency content of the oscillations of red giant stars to try and predict parallaxes and see how well this works. So this is work led by my postdoc Sanya Khan. One paper was recently published, the other from which this plot is taken will be submitted very soon. And basically here we have a view of the sky of different fields where we could actually measure these frequency spectra of about 12,000 red clump giant stars. And the astroseismic frequencies that we measure can be interpreted through stellar models when we also plug in spectra and photometry to basically give us the luminosity, the bolometric luminosity, which we can then turn into a predicted parallax using the apparent magnitudes. And if we compare that to the measured parallax, which is here the Gaia parallax, this is the offset determined by Lindegren, and this is our prediction, then we see that, for example, in the Kepler field, that's this white one up here, that is where we have the best data, and that's just a function of the time span of the measurements of 4 years. In this range here, we have essentially no additional residual parallax offset. That makes this magnitude range here particularly interesting because if we can have stars in that magnitude range where we know the parallax, we don't need to solve for the parallax offset anymore, and we can use the parallaxes to maximum advantage. We're also seeing some other effects in this diagram. The yellow line is unfortunately biased towards one particular type of red clump star. Those are some details I'm happy to give you the information about later in questions. But for example, here on the bright end, unfortunately, what we're finding is that we don't have enough bright stars over the entire sky to really calibrate this bright end. And so there are still some systematics in the Gaia solution for stars, let's say, brighter than 11th magnitude. And if you're interested in using those, you should be careful. So now that we can have stars in the magnitude range, let's say fainter than 11, we actually are very interested in using star clusters. Here you see an example. And we use, so my PhD student Mauricio Cruz Reyes mined the ESA mission Gaia to find clusters that are in the vicinities of Cepheids. And the reason is that what we want to do is we want to replace the parallax measurement of the cluster with the average parallax, the parallax measurement of the Cepheid with the average parallax measurement of the cluster. And we benefit here from an improvement in statistical precision because we can average over hundreds to about 1,500 stars in the biggest case. And we have the best understood systematics, as I showed you previously. So with this analysis, we found about 34 of these. And a typical error in these average cluster parallaxes was 7 micro-arcseconds. It's always a good idea to give a sense of scale of what that means, and it's about the size of a small coin on the surface of the moon observed from Earth. So this is the accuracy of these parallaxes that we're measuring. If we plug in these 26 clusters together with 225 field Cepheids, we got about a 0.9% calibration of the luminosity scale of Cepheids, as well as the 6 sigma detection of the residual parallax offset. And then going forward in the next Gaia data release, because the proper motions will be so much better and we will be better able to identify the host clusters, we hope to get to about a 0.4% calibration using Gaia in the Milky Way of Cepheids. Then, as Adam mentioned, there's about 17 of these stars that have HST photometry, and it's really impressive in this diagram here. You see the red points are the cluster Cepheids, the gray points are field Cepheids that have HST photometry, and the improvement in the scatter is about a factor of 2 between the field Cepheids and the cluster Cepheids. And in fact, this 0.07 magnitude standard deviation here is the same as in the Large Magellan Cloud, where you have all the Cepheids at the same distance, and you can just look at them as projected onto the surface, onto the celestial sphere, whereas here we have all the objects at various distances. That just shows you how accurate these parallaxes are. And because of their small errors, essentially one cluster Cepheid has the same weight as 9 field Cepheids. So in Adam's work and in our work, we actually did a different astrometric processing. So we had different lists of membership for the same clusters, and we only came out at an average distance difference of about 5 micro-arcseconds. And combining our measurements, we get to this value of the Hubble constant, which corresponded to a 7% reduction in uncertainties and an increase in the tension with Planck to 5.3 sigma. So more recently, I've also been looking at some of the systematics involving the TRGB measurement, and in particular, the absolute calibration. Now remember, what we're looking at is this feature here, this blue line, which is measured actually by calculating the derivative. This is the red curve right here, the derivative of the luminosity function. So the luminosity function is just the marginalization over magnitude that you see here. And one of the issues involved in this measurement is that, of course, the actual luminosity function here is this jaggedy, noisy histogram. You need to smoothen out that histogram in order to calculate a sort of noise-limited tip of the red giant branch magnitude, which is defined as the inflection point along that luminosity function. So the reason we wanted to do this is because you may have seen plots of a similar kind where you have, of course, the early universe measurement for the Hubble constant and then the late, which depends on lambda CDM, and then the late measurement that is direct and model-free. And there's been this TRGB measurement with larger uncertainty that has kind of been falling in between. And the big question is, well, does this tell us something about the uncertainties of the TRGB, or does this tell us something about the tension? So what's really going on here? So we focused our attention in particular to the absolute calibration in the Large Magellanic Cloud. And one thing that we found is that in this color magnitude diagram, so magnitude and color, this is the red giant branch here highlighted in density and with a contour, that all the stars, as you go up to the tip, which is the horizontal line here, are variable stars. This is not something that was previously considered in the measurement, but it's a consequence simply of the stars becoming larger, more convective, and as it turns out, there's actually multiple period luminosity sequences that you can see here. This is log P, and this is the K-band magnitude in the LMC. There are multiple PL sequences that are quite reminiscent of what the Cepheid period luminosity relation looks like. And so this is exactly what we're drawing from here. But it just turns out that all the stars at the tip are variable. And in particular, this realization allowed us to filter out objects that we're not interested in, the stars that are not really nearby the tip of the red giant branch. And you see the difference here. The blue luminosity function is the so-called all stars luminosity function. So this is just using all the red giant stars as is commonly done, versus the black line, which is the selection of only the variables. And it turns out that the black measurements here, this is a representation of the TRGB feature that you measure as a function of a smoothing parameter that you have to apply in order to calculate the inflection point. This is a methodological choice you have to make. It's kind of an arbitrary number you have to select. And of course you want your measurement to be insensitive to this. If it's not insensitive, you could have a bias. And what we show here is that the OSAR, so the variable star luminosity function, over a very wide range is insensitive to the choice of smoothing, which is of course a desirable feature. Whereas, for example, the all-stars luminosity function, because of its increasing tail here to fainter magnitudes, it's actually very sensitive to that bias. And so we supported this with extensive simulations to also show how contrast and the steepness of the TRGB are affecting the measurement. And in the process, we figured out that, well, the tip of the red giant branch is actually more like some twigs of a red giant branch. So twigs are, of course, the smaller sort of subdivisions of an actual branch. And you can see this here by looking at the different PL sequences. And in particular, I would like to focus on A and B sequence here. But of course, in the overall OSAR measurement, we've just been using all of these. But if we look at this A and B sequence in particular, here we have the logarithm of the period and the magnitude. Red and yellow encode the two A and B sequences. Blue is the overall all-stars red giant branch measurement. You see that the luminosity functions look quite different. The red one is much more skewed and much sharper at the tip. The yellow is actually at a lower magnitude, and you see it visually in this diagram where the tip of the red giant branch magnitude would be measured. And if we look at it statistically, they're different at 4.5 sigma significance. So this tells us that within this tip of the red giant branch that we always thought was just one stellar evolutionary phenomenon of stars moving towards the helium flash, and then they will move away, we actually have a significant diversity of the population that could lead to different magnitudes measured on different sets of stars. And so this is quite a thorny problem then, because different types of groups of red giants will be differently populated by these different populations. So let's now move on to how we actually apply the absolute calibration when we measure the distances. This is what I mean by ensuring the equivalence between rung 1 and 2, because of course if you calibrate your standard candle using known distances on one end, and you apply it at another end, you need to make sure that the objects are either the same or that you can somehow mitigate the differences that there are. And as Adam mentioned, there's lots and lots of work that's already gone into this, how to get rid of the dust problems, or even the metallicity effect is very recently clarified. Binaries were discussed as a possible source of worry for a while, but they're really not a problem. There's some very good work on this. Today I will briefly mention three things, one being something we like to call stellar association bias, some relativistic effects, and then the TRGB standardization. So stellar association bias has to do with Cepheids occurring in star clusters. I mentioned this earlier, we can use this to get a better absolute calibration, but if you consider that a gravitationally balanced system has a physical scale, that physical scale becomes unresolved by your fixed detector element at some distance. And so your photometric uncertainty, your photometric background estimates are no longer sensitive to that effect. So what we're doing here is going beyond an earlier study we did in 2018, and we're actually looking at M101, that's the closest type 1a supernova host, and we're looking at UV images. Here you see the postage stamps of just 5 Cepheids in the UV, then V band and I band, and we're simply counting how many of the Cepheids in that galaxy are associated with clusters, and how much, that's this FCC here, the fraction of cluster Cepheids, and then we measure how much the light contribution of these clusters is actually shifting the period luminosity relation from where it should be. That's this distance bias here. So in M101 we find about, this is work done with Zoe Spezieri, my postdoc, and Bastien Lang, my PhD student, and we find a fraction of cluster Cepheids of about 7.5%. And we also see that it varies quite a lot spatially over the region of these two footprints shown here in yellow. There's also some work on this based on M31 and M33, which all showed a smaller fraction of cluster Cepheids, but we find that M101 is more comparable to the Milky Way in that regard. So clearly there's some variations of this, and luckily we also have UV data for HSE 4258 to do the test there. So basically what we can do, thanks to this inventory of Cepheids associated with clusters and those without, we can fit period luminosity relations to the two samples separately. So the red line here is the cluster Cepheids, the blue one is the field Cepheids, and we find a difference, a typical difference of about 1/4 of a magnitude per cluster Cepheid. So this is this term delta mu here. But if we multiply it by the 7.5% fraction of Cepheids in star clusters, what we find is about a 0.02 magnitude difference. However, Cepheids that cluster with their host clusters means that at greater distances, the light of the cluster is actually preventing us to identify the Cepheids, because we're identifying the Cepheids through the light variability, which is using the flux ratio between when the star is brightest and when it's faintest. When you're adding constant flux, the amplitude goes down and you no longer detect the Cepheid. So what we did here is we deprojected, or we projected the images of M101 to much longer distance, repeated the analysis, and applied all the selection criteria as they are applied in the other SHOES supernova host galaxies. And what we see is that the cluster Cepheid fraction of the Cepheids we're still able to recover goes to 0. So that actually means as we're going to longer and longer distances, this term up here goes to 0. In other words, there's not really much margin for this to contribute to the distance ladder. And in addition, there's already a 0.007 magnitude correction applied in the current SHOES distance ladder based on our earlier result from 2018. So really what we have here is an upper limit to a possible reduction of the Hubble constant that is of order 0.5%. But it's an upper limit because, well, the cluster Cepheid fraction decreases to longer distance, and the HSE 4258 galaxy also is similar to M101 in this regard, but will push the bias in the opposite direction. So as a reminder, the Hubble constant tension is of order 0.17 magnitude, and clearly this residual of 0.012 is not going to, well, get rid of the Hubble tension. However, this type of work, of course, helps us sharpen the uncertainties and have confidence in the statements of the systematics. We also looked into relativistic effects and how they may actually end up biasing the results. And I see a couple of people smiling, so you recognize this from Back to the Future. Essentially, Cepheids are clocks. We're measuring periodicity of variability, right? So this is just time. And we know from special relativity that clocks and moving inertial frames are subject to time dilation. So this measurement of period here is really biased by cosmic expansion, and the more distant Cepheids appear to have longer periods than they really have in reality. So if we're truly interested in this point here, which is the absolute magnitude at the true period, but we have an apparent magnitude at the observed period, we first need to get rid of the time dilation feature in order to make sure that we're getting the right distance. And it's funny because this kind of effect, actually, before it's corrected, would have underestimated the Hubble constant, so correcting the relativistic effect here ends up increasing the value of the Hubble constant, and is already accounted for in the Schutz distance ladder since its last installment. We also looked at K corrections. Those of you doing galaxy science will know this, of course. This is simply the way that light is redshifted and the part that you measure. And so what we did actually was to do a forward simulation, placing the source with its spectral energy distribution in the emitter frame, extincting it in the emitter frame, then redshifting the light, then applying foreground estimation of some redding, and then comparing this to what the empirical typical correction is of something that, for example, uses a known color and then tries to get rid of the extinction effect without correcting the K correction. And what we see here then is the amount of K correction that is still needed as a function of redshift, or here in distance if you prefer megaparsecs. And the different lines here show you different filters. So the optical filters typically lead to negative K corrections, but the infrared filters lead to positive K corrections. And in particular, this dashed black line right here, that is the Schutz near-infrared Wesenheit magnitude that combines an H-band and a V-I color. And so it turns out to be very flat in this regard because you're compensating different effects, one coming from the optical and one coming from the infrared. On the other hand, if you're looking for just James Webb filters, single-band filters, and you want to go to 100 megaparsec, let's say, using the JEGB or the typical giant branch method, you all of a sudden have about a 1% bias at that distance level if you're using a single filter measurement. So you should be really careful if you want to measure the Hubble constant using TRGB or JEGB with James Webb, because you will need to correct for these effects in order to get to 1%. So a quick summary of the relativistic effects and their impact on the Hubble constant. We looked at three different things: time dilation, decay corrections, and one more thing, which is the effect on the reddening slope that is used to calculate the Wesenheit magnitudes. All of those are really small. The largest of them is already included in the Schutz Hubble, in the Schutz distance ladder. But of course, if we go to larger and larger volumes to get more and more type 1a supernovae, these types of effects become more pronounced. And in particular, for James Webb, it could be of order 1%. So, coming now to how we apply the tip of the red giant branch in these supernova host distances, Adam already mentioned that there is some standardization required. And in particular, this has to do with the way that this inflection point here is measured. So there's this work by Jeshi Wu in 2022, where using the ghost galaxies, essentially you can place halo fields in the vicinity of a galaxy. So the TRGB method works best when you're looking at really old red giant branch stars, metal poor, very old stars. So you want to go out to the distant halos. It's kind of counterintuitive for people who don't do these measurements, maybe, that these fields do belong to the same galaxy, of course. So what you find empirically in this type of measurement is that you get a relation between the ratio R, that's the contrast, counted simply as the number of stars within a certain magnitude range below and above the tip, that the actual measurement of the tip magnitude depends on this value of R, and this the size of the effect is about 0.02 magnitude per unit of R. So this is unfortunate. Well, it's good that we now know of it and that we can correct for it, and of course including this together with the type 1a supernovae from the Pantheon Plus sample allowed to measure the Hubble constant to 73.2 plus or minus 2 kilometers per second per megaparsec. But using our simulations from the LMC calibration I showed earlier, this is very preliminary work because it's something we're working on in response to the referee report. We basically figured out that this tip contrast ratio is a direct consequence of a weighting that is applied to the edge detection technique that seeks to measure the inflection point here. So this is sometimes called the hat Sobel filter or something like this. It basically weights the Sobel filter response by the square root of the number of sources, and it ends up creating this tip contrast ratio. So in the red line here, for example, you see the signal to noise weighted edge detection technique versus a normal Sobel filter that does not apply this weighting. This is the magnitude bias, and this is the contrast ratio. You very clearly see that essentially it's this weighting that introduces the tip contrast ratio. And in addition, from our simulations, we find the same magnitude. It's 0.021 plus or minus 0.003. So it's fully consistent with what is found empirically, even though here we simply recreated the luminosity function of the large Magellan cloud, and then what we ended up doing is varying the height of the HGB feature to basically reproduce these different contrast values. So this is really good because we now understand where this tip contrast ratio comes from. It's not an innate property of the stars, it's a property of how the inflection point is measured using the edge detection technique. What we also see is that the Ozark luminosity function, so these are the variables, is actually less sensitive. It's about the contrast ratio, the tip contrast relation is only about half as pronounced as it is when you use all the stars, and that comes from the fact that here you have the increase in the luminosity function, and the Sobel filter actually ends up pushing this down. And then one last thing I'd like to briefly mention is that the TRGB also is very sensitive to where you actually do the measurement of the stars. So here in a paper we had recently in the archive with a PhD student from Munich, Geza Czerny, we looked at M51, the Whirlpool galaxy that is host to a type 2P supernova. And Geza with his collaborators were able to measure a very precise expanding photosphere method distance to this supernova. So this is essentially looking how the angular diameter changes and how the linear radius changes to measure geometric distance, which is accurate to about 3 to 4%. And for the Cepheids in that galaxy, we don't have infrared measurements. That's why the uncertainty on this galaxy is slightly high, about 3%. But we find perfect agreement between the supernova distance and the Cepheid distance in that galaxy. But it's quite off from where the TRGB was in that particular galaxy. And that's probably a consequence of the TRGB field being located on the spiral arm of that galaxy, where you have lots of young stars, metal-rich stars that are exactly not what you want when you want to get a very accurate TRGB distance. So a few, summarizing a little bit the statistics I was just telling you about, well, for the Cepheids, we've been putting in a lot of work on exactly this, trying to see where are the possible changes that could worry us at the 1% level, but we don't find anything that is really of concern. We see metallicity effects, we see this clustering bias, we see relativistic effects and so on, but all of those are controlled now at the level of 1%. So I think this 1% measurement is attainable in the future. The TRGB systematics, I think, are improving, but they are quite complex. We're seeing to some extent, new features that we're not too familiar with in the past, and I think most of what this relates to is the fact that it's a statistical standard candle. You're looking at a population of stars you don't control, and of course that leads to some problems. For example, the diversity of the populations, as you can identify from the variability, but also where you measure it, the shape of the luminosity function, and then even how you calculate the edge detection response. So further cross-checks between these different methods are really useful. We're going to have multiple galaxies where we can calibrate the different standard candles together. And I think all of this, of course, will go towards more accurate distances to type 1a supernovae, which will then afford better Hubble constant measurement. So where does this all lead us for the value of H naught? Well, we have the most accurate parallaxes from Gaia with the cluster Cepheids. We're looking, for example, at the clustering bias. We really shouldn't ignore, I think, this population diversity of the TRGB, although it's so unfortunate that the variability is not really large enough to discover it at very long distances. So the local universe will remain our probing grounds for that. Once the empirical standardization of the tip contrast ratio and the type 1a supernova treatment is done consistently, you get to a value of the Hubble constant that is fully consistent with the Cepheids in the late universe. And so I would really say that there is not currently any disagreement between late universe probes of the Hubble constant and the TRGB and the Cepheids are reconciled. And those interested in using that method in the future should also be worried about K corrections at the level of 1%. Thanks very much.
Adam, if you want, you can go.
Can you hear me?
I can hear you, but I don't think you're on speaker.
Just put your microphone close to the...
Okay, one second.
Can Richard, can you hear me?
Yes.
Okay, great talk. Very interesting. I hadn't seen that work on Tip of the Red Giant Branch and the simulations of how you could explain the tip contrast relation, but we've seen similar things, so that makes sense to me. We have thought that most of it may be from the measurement process rather than astrophysical. My question to you, though, is you talked about how it's the noisiness and the attempt to weight the edge that is producing this. Of course, that's done to increase signal to noise. So my question to you is one better off using an unweighted edge detection and sort of just living with the poor signal to noise, or to use the weighted version and then I guess I would say de-bias it with the tip contrast relation?
Yeah, excellent question. I think my take on this would be the important thing is you're doing the same thing. So when you're calibrating the absolute magnitude and when you're then measuring it, it has to be done in the same way. What we do see is that the unweighted Sobel filter is less sensitive to this kind of effect. So probably you wouldn't then have to actually take into account the tip contrast ratio because the measurement itself is insensitive to it. But of course, if you want to compare it to, let's say, apparent magnitudes of the TRGB in galaxies that have already been measured, then you need to make sure that you're using the exact same instance of the edge detection response. So making sure that it's weighted or unweighted depending on what you're looking at. My favorite would be to use an unweighted procedure, and we have similar effects like that if, for example, we're, for example, if you want to measure the mean magnitude of a star, right, and the magnitudes vary a lot, and if you weight them by the flux error, you're actually introducing a bias. And I wonder if this is not one of these same kind of instances. It can be calibrated out with the tip contrast ratio, but I think the best thing would probably be to ignore it altogether and just use a regular Sobel.
Very explicitly now, and Adam's here. And so basically, if you split the Cepheids on the sky, right, in the hemispheres, you find a large variation in magnitude. Now, the question is that a statistical fluctuation in a small sample? It's much larger than the stuff you're talking about. And it leads to something like a 4 kilometer per second per megaparsec variation in H0.
Is there a question?
Yes. So the question is, that's a much larger effect than these small corrections you're talking about. Now, the question is basically, the question myself and Adam have been wondering about, is that a statistical fluctuation in a small sample, which you can always interpret that way? Or is this something we should worry about in the context of other observations that we're finding? The question is basically this: do you think you can measure H0 with 1%? It's on the slides.
So I think, as Adam said, this question of whether or not you can measure the Hubble constant to 1% in the end is about the supernovae and how they're, how they trace the Hubble flow. Because the Cepheids don't measure the Hubble constant. The Cepheids provide you the absolute calibration of the supernovae, right? They just tell you their luminosity. They don't go far enough in the distance, and I have some trouble splitting Cepheids into different hemispheres because even in the Milky Way it spans 2 hemispheres. So, yeah.
Right. So the problem at the moment is that we have very few Cepheids, right? As anchors. Now, can you imagine?
There's 42 type 1a supernovae and 37 hosts.
Right. So it's a small sample. But can you imagine a calibrator where we could have a larger sample where potentially we could split them on the sky and see if there's a variation? Now, bear in mind that basically we correct everything for CMB dipole, right?
I think if there is a way of getting more objects that help you precisely measure the Hubble flow, people will be all over that.
I think it's Adam want to add something.
Adam, go ahead.
Yeah, I can just weigh in a little bit on this. I think all the ideas about cosmology that Jon has and others about dipoles, as Richard said, is about the supernovae. This hemisphere variation that you're describing pertains to the hemisphere in which you calibrate supernovae with Cepheids. Because they're both located in the same galaxy, redshift doesn't play a role. So any theory you have about the Friedman equation or cosmology doesn't play a role. I mean, you can imagine all, just for argument's sake, all the Cepheids could be with supernovae in the Virgo cluster, for instance. And so, everything would be located in one spot. That wouldn't change cosmology unless you have a theory. I don't even know how that theory would work, where the hemisphere causes an effect on calibration. It would be like saying, what hemisphere is my telescope in on Earth? Do I have to look at the variation by hemisphere of telescopes I've used? It's not tied to an idea or theory, and all the ones you have about cosmology are only going to involve supernovae. They're not going to involve the calibration.
Just a comment first of all on this. There's a simple idea where you have a hemisphere in anisotropy, in which case you are an off-center observer in a spherical distribution, where you naturally will see some anisotropy between 2 hemispheres. So there are some theoretical ideas which would justify it. My question is the following. Have you tried to test the robustness of the period-luminosity relation and the metallicity luminosity relation with respect to various distance beams?
Various distance what?
Distance beams. Beam this in various distances and see if it's consistent among different beams.
I don't think that this has been done as a function of distance bins. What is done is that the H2 regions in the various supernova host galaxies are used to determine what's the difference, to correct things. But I don't think that this has been split up into distance bins. Yeah.
Sorry for the naive question, but what is the difference with results by Friedman?
Yeah, so the difference is essentially, so the point that's shown here as Anderson 23, the difference is in, there are 2 main differences. Both have to do with the absolute calibration of the TRGB coming from the LMC. One is the use of the reddening law. That is slightly different in that we actually did the synthetic photometry specific to the counting the source spectral energy distribution that was not done by the previous work. And the other thing is that we have a different measurement for the apparent magnitude in that galaxy, and that seems to come from the way that the Sobel filter is calculated. So in the revision of the paper, we will probably have to we'll probably move that measurement because of exactly what I mentioned earlier about how this weighting of the Sobel filter ends up shifting results relative to the unweighted results. Then in the work here by Skolnick, the main difference comes from the type 1a supernovae that has to do with the peculiar flow corrections from the Pantheon Plus and the cross-calibration of the different type 1a supernova samples.
Respect